Good morning, everybody. It's a pleasure to be here, although the hall is half empty, but it's okay. I want to congratulate the Solid State Institute and the Physics Institute of Belgrade and of the Academy of Sciences, the Serb Academy of Sciences, and the Solid State Institute in particular, which celebrates its 30th anniversary. And I'm very glad that I could, in a small way, could contribute to that by educating Dr. Bojana Vicic in my laboratory. And she came back a few years back to Belgrade, and she started her own positional research group. And I understand that she's doing very well now in her research. So with that, let me start my presentation. So what I'll tell you is about inorganic nanotubes from tungsten disulfide to misfit layered compound. So the idea of 2D materials is not new, but it goes actually back 100 years ago to first paper by Linus Pauling in 1923, where he determined the structure of molybdenum disulfide. But nowadays we are able to, first of all, to synthesize many of them, and we will hear some talks about synthesis of new materials in this class of materials. So layered materials or 2D materials are basically materials that are made like a deck of cards, card on a card, with very strong covalent bonds in the layer and very weak van der Waals interaction between the layers. And there are many kinds of layered 2D materials, probably 10,000 if not more. And what I would like to put your attention is to the work of Linus Pauling. So my first few slides will be introductory, basically. So this is the work of Linus Pauling, which was published in 1930. And he distinguished actually between two kinds of layered compounds. He said there are two families of layered compounds, the symmetric and the asymmetric. The asymmetric, like the one, I'm not sure, is there a laser pointer here? Do you see? Okay. The asymmetric ones are like alumosilicates. They have different, they are silica or oxygen structure, oxygen binded to silicon in the middle, and the lower ones are octahedra of manganese or aluminum, and so these are kaolinite or chrysotile, and then due to this asymmetry, they tend to bend and form nanotubes. And while he predicted it from X-ray, he was not able to see that via electron microscopy because he didn't have electron microscope to see these structures. And the other class of materials, that symmetric one, they have the same axis or the same lattice size on this side, like mica, and on this side. So you have a deck of cards or pages which are either asymmetric or symmetric, and the asymmetric do not form nanotubes. The asymmetric form nanotubes, that's what he said, due to the strain, and the symmetric one do not form nanotube, and that's what also he said, and he was wrong, of course. And we know now why. And the pioneers were actually Krotos, Smolly, and Kerr, who found the C60 or discovered the C60, which is a structure made, a hollow structure from carbon. And if you think about it, then came Ijima, who discovered in 1991 the carbon nanotubes, or rediscovered because they were already known in the literature, but he really interpreted the structure and understood that basically the structure, this graphite, if you bring it to the nano size, there are so many dangling bones on the edges that they will not be stable as flat surfaces, but rather try to close their structure into a nanotubular structure, or C60 in the case of 0D materials. So with that notion in mind, I went to propose this also for molybdenum disulfide and tungsten disulfide, because they are layered compounds like graphite, and they suffer from edge effects similar to graphite. So you have these layers of tungsten disulfide with tungsten in the middle and 2 layers of sulfur in the layer, and then weak van der Waals interaction between the layers. And if you look from the top, you see that there are many, many dangling boats around this nano structure of molybdenum disulfide or tungsten disulfide, and consequently, they remain unstable. And if you heat it up to 900 degrees or so, they will spontaneously form nanotubes. And that's what we saw. So here is the picture of or some of the first early fullerene-like structures. So these are the equivalent of the 0D C60, but they are not, because they are much larger, there are many layers, and they have many defects. But the important point here is that each layer is folded on itself. Each black line is a layer of tungsten disulfide or molybdenum disulfide, and they form a hollow closed structure. And whatever angle you tilt it, you see the same kind of picture, and you see also the diffraction remains the same. And it took us many, many years to learn how to produce them as a pure phase, because usually crystals want to grow, or energetically they favor large material with small surface, large crystallites. And we had to do some kind of an arrested growth in order to be able to synthesize these materials in large amounts and in pure phase. And once we had it, we started to study their properties. Here is an example of a recent paper that was published by us. This was a work of Wojciech Kundrat, who is now a PI in Masaryk University in Brno. And while he was a postdoc with me, developed a synthesis to produce nanotubes which are as long as 0.5 millimeter or close to millimeter. Tungsten disulfide, which is the first time we get nanotubes of this length systematically. And you see these nanotubes, how perfect they are in terms of their structure. And here he describes the oxide, the W5O14, that is the precursor. So he starts first by growth of precursors of long nanowhiskers of tungsten oxide, suboxide, and then he sulfurizes them, and he gets this beautiful mesh of nanotubes, and with that he can make a kind of a web or a page or whatever you can call it, a membrane with which he could filter heavy metals by using a solution allowing the solution to go through this membrane, and he purified solutions from heavy metals like gold or silver. So this is the first example that we show of very long and pure phases, almost pure phases of long tungsten disulfide nanotube. And they are always multiple because the energy of curvature is about 10 times larger than that of carbon nanotubes. So for carbon nanotubes, it's very easy to fold on itself and form single wall nanotubes, which is quasi impossible for molybdenum or tungsten disulfide or other inorganic layered compounds, because they are thicker and it takes much more energy, about 10 times more energy to fold them per atom. So here is the paper that describes this work. And I want to go into another paper which was published by Professor Alazak from a nearby institute. She's a graduate of my laboratory. And here she studied how to synthesize molybdenum disulfide nanotubes systematically. So if you start from tungsten oxide, you use tungsten oxide nanoparticles, and they elongate into nano whiskers, and very easily they are sulfurized between 800 degrees to 900 degrees. And this is not possible for molybdenum oxide because molybdenum oxide evaporates at around 700 degrees. It sublimes, basically. So what you do, and what she has done beautifully, was to heat it gradually from 500 degrees to 850 degrees, and then also change the composition of the gas so that it will go from reducing hydrogen-rich gas into a sulfur-rich gas by H2S when she elevated the temperature. So in this way, she was able to get the first pure phases of molybdenum disulfide, which was a great accomplishment, I believe. Let me go now into a very interesting recent paper of, again, Dr. Wojciech Gundrat. And the reason that I show it is not because we have nanotubes. We already know that multi-wall tungsten disulfide nanotubes are very easily obtained. But now the synthesis is done in situ in the electron microscope. So imagine for yourself a microreactor that is placed in the SEM, and then the microreactor works at few millibars of hydrogen sulfide pressure flow and hydrogen and a temperature of close to 1,000 degrees, actually 1,000 degrees. So if you think of that, if this hydrogen sulfide will evaporate from the microreactor and leak out from the microreactor, in about 5 minutes you will have no microscope. So this is a first time that you can really show that you can do a microreaction in the electron microscope. Within the electron microscope, you can take this stub or this grid from the SEM to the TEM and look at the high resolution reaction at every step and how the reaction is progressing. And I won't go to the details, but we have actually promoted here a new growth mechanism from the nanotubes. Before, we always thought that the hydrogen comes from the outside and goes inwards, like you can say Kirkandel effect, but now we see that there is also remains of the tungsten oxides, since it's engulfed by tungsten sulfide layers, there are tungsten oxide also in the core, and consequently, they react with the hydrogen sulfide that goes into the core, and the reaction progresses inside. The tungsten disulfide is not only formed from outside in, but also inside, and we could verify this reaction or mechanism using this beautiful microreactor. This microreactor is now fabricated by Thermo Fisher. It was a joint work with Thermo Fisher, and I think we actually bought it in the institute, in my institute, but they are developing it for other reactions as well, and so this is possible now to do a different reaction in situ in the electron microscope. Let me go also to another recent work of Dr. Gundrat, and this is the core shell nanotubes. So the idea here that if you want to take a tungsten oxide, for example, whisker, I told you that it's very stable, and you want to react it directly with with hydrogen telluride or hydrogen selenide, it will not be successful. You can do that maybe one or two shells, but the problem is that when you heat it for 900 degrees, at 900 degrees C, in the presence of tungsten ditelluride, in the presence of hydrogen telluride or hydrogen selenide, they slowly collapse and the nanotubes is not forming. So what is the idea that he took? He took the following path. He took the tungsten oxide whisker, coated it with few layers of tungsten disulfide. So again, from outside in, there are few layers of tungsten disulfide that form and coat the tungsten oxide core. Now the core is stable and you can evaporate the tungsten ditelluride or with hydrogen telluride or with hydrogen selenide, either from outside, and then you get a tungsten ditelluride coating the tungsten disulfide core, or you can even do that inside. So here in this case, you can have both tungsten ditelluride inside and outside. And the beauty of this work is that it allows us to get tungsten ditelluride or tungsten diselenide, which are very important quantum materials, especially in the 1T form, which you see here. It's a complicated story, but actually this paper is submitted now, and there is a following paper on tungsten diselenide nanotubes, which are synthesized in a similar way. And there is a transformation of phase from 1T to 1T prime when you go from the bulk tungsten. So this is the tungsten disulfide, and this is the tungsten ditelluride, and it transforms gradually from 1T to 1T prime. I won't go to the details, structural details, but this is very beautiful demonstration of the core shell nanotubes that we can do today. And there are other techniques and other technologies to produce core shell nanotubes. For example, if you want to use chlorides, many of the halides or hydroxides are layered compound, and you can do the reaction in the presence of, for example, molybdenum chloride, and you can get molybdenum chloride layers coating the tungsten disulfide, or for that sake, you can also take carbon nanotubes. And there is a paper just published on that, using for chromium iodide, which is also a very important magnetic quantum material coating in carbon nanotubes. So with that, let me go to my next part of the talk, and that will also deal with the electrical properties and optical properties of the nanotube. Dr. Lena Yadgarov, who is here in the audience, will expand on this in her talk in the afternoon, I believe. But first of all, I want to show you a few very important consequences of the effect that you have a nanotube and not flat layer. So you know very well that when you take tungsten disulfide, it's an indirect band gap transition with an indirect band gap transition of about 1.4 electron volt. And when you exfoliate it into a single layer, owing to the quantum size effect, you get, first of all, you get a direct transition, which is much larger, about 2 electron volt or 2.5 electron volt, compared to the monolayer or multilayer tungsten disulfide or molybdenum disulfide, for that sake. And in the case of nanotubes, the story is completely different, because you have the strain effect, and the strain effect overcomes the quantum size effect, and you see that the band gap, instead of increasing, goes down, owing to the strain that in the nanotubes, which get smaller and smaller. And to prove that, one of the techniques that we have used was to use excitation Raman. And excitation Raman is you stand on one Raman line, the A1G or E2G, and you change or you vary the laser wavelengths of your excitation, and you see how the band gap or the edge of the Raman line varies with the diameter of the nanotubes, and you see that clearly that the diameter shrinks when the band gap shrinks when the diameter gets smaller. So this was a very nice demonstration of the shrinkage of the band gap owing to strain effect in tungsten disulfide nanotubes. And let me go now to another effect. This is the bulk photovoltaic effect. So we studied several optical and electro-optical effects. We are not experts, so we always collaborate with research groups, other research groups. So in this case, we actually use the fact that tungsten disulfide they don't have inversion symmetry or mirror symmetry. They are asymmetric in that sense, and they also do not have time reversal symmetry, namely the current in one direction is opposite to the current in the other direction if you apply a magnetic field or not magnetic field, if you apply the current, photocurrent in the laser with the laser. So basically, the loss of these two symmetries, the inversion symmetry and the time reversal symmetry, lead to effect, photocurrent effect, not at the junction. So usually when you take multi-wall tungsten disulfide or even single-wall nanotube, a single-wall tungsten disulfide, the photocurrent is always at the junction with the gold electrodes. But in the case of the nanotubes, you can get the photocurrent in the middle between the electrodes. And this is the classic demonstration of the bulk photovoltaic effect. And this bulk photovoltaic effect was orders of magnitude larger than the known bulk photovoltaic effect in nanotubes. So this is a work in collaboration, or mostly done in the laboratory of Professor Iwasa in the University of Tokyo. And so it demonstrates a completely new photovoltaic effect, which was known, but was orders of magnitude less. And the beauty of these nanotubes is that due to the loss of these symmetries, they demonstrate this effect. Another very beautiful paper, which was published a few years back, a collaboration with Professor Yao Gao in the Beijing Institute of Technology. We have now another paper in submission on electro-optical properties of the nanotubes. So here, you take a nanotube and you apply a voltage. And when you apply a voltage, because you have multi-wall nanostructure, some of the nanotubes shrink, some of them expand, some of the walls shrink, expand, and you basically form a dipole. And this dipole is stable because there is enough friction in the system that you have to apply a very high reverse voltage in order to release this dipole in one direction. So if you illuminate these nanotubes and you scan the voltage in very small span, you get an asymmetric IV curve. Namely, in one direction you get this current, and the other direction you get this current due to this dipole, remnant dipole that is exists in the nanotubes which were first apply under high voltage. So you first apply the high voltage, and then you start the photovoltaic measurements. And you can see it's a piezoelectric effect, also due owing to the loss of symmetry, inversion symmetry in the nanotubes, and you get a hysteretic IV curve, which can be used as a memory effect, or you can think of it as a memory effect, which can be reversed by applying a reverse high voltage. So you see this beautiful hysteresis behavior, and now the next step was to take these nanotubes, spread them on silicon substrate, and use lithography in order to print different contacts, 4x4 contacts, a matrix of 4x4 contacts, and apply this photovoltaic effect, or measure this photovoltaic effect in this pixels on each pixel. And using machine learning, he could see, and I'm not an expert in machine learning, but using machine learning, he could train the system to remember the signals of different words. And in this case, he chose the word Zion, so he recorded the word Zion on Z-I-O-N on this array of nanotubes, and then he retrieved it using a capacitor and high voltage. He could retrieve this information and print the word Zion on a piece of paper using a laser and a capacitor, discharge of a capacitor. So you have a beautiful demonstration of new possibilities of multi-wall nanotubes, which are very different from single-wall nanotubes, and they have their own advantages using the fact that you have multi-wall structure. So with that, let me go to the other part of my talk, and these are the Misfit nanotubes. So what are the Misfit nanotubes? The Misfit compounds are known since many years, 60 or even 70 years. The structure was elucidated about 45 years ago by Makovitsky and Hyde. And basically, these are non-stoichiometric layered structures. And the fact that you have Misfit here is owing to the fact that the lattice constant of, say, lanthanum sulfide is different from that of tantalum disulfide. So they have a common C-axis, they have a common B-axis, but the A-axis is different, and it's irrational number, and consequently it's an astoichiometric or non-stoichiometric compound. And they are layered pairs of compounds, they are pairs. And you naturally, from my first slide on the work of Linus Pauling, you know what happens to asymmetric compounds. They bend immediately, spontaneously, and they form nanotubes. They can form nanotubes. And if you apply these two effects together synergistically, namely the bending due to the strain and the edges and healing of the edges due to this nano effect, you get beautiful nanotubes using high temperature CVT process. I won't go into the details of this process. You use a catalyzed tantalum chloride and you move this misfit compound from the hot zone to the cold zone, and you get nanotubes. We got hundreds kinds of, I believe, close to 100 kinds of nanotubes from misfit compounds, and you can see them, how beautiful they are, long, uniform, using EDS mapping. You can see that they are uniform. You can see their structure to the latest detail, namely, if you slice them through with a fib, you get a slice that, and you can watch the structure in a very detailed way, and you see how the model agrees so well with the predicted structure. So, as I mentioned, we synthesized over the last 13 or 14 years, we synthesized many such nanotubes, and some of them are superconducting. Especially we deliberated in recent years on the lanthanide or rare earth-based nanotubes, and you see they are superconducting at about 5K degrees, and this is 1D superconductivity is very different from regular superconductivity. And I don't want to go into detail, but we published a very nice paper with Ivasa on the difference between 1D superconductivity of nanotubes and 2D or 3D. And so, how much time do I can stop? Okay, because I started a few minutes after 9. Okay, I'll just very briefly show. So a recent work which was published with my student Sridhara, we simply replace sulfur by selenium. And you think that at this elevated temperature of 1,000 degrees, the sulfur and the selenium will distribute in the lanthanum sulfide, tantalum disulfide indifferently. I mean, they will spontaneously go randomly into different webs in different sites, and in fact this is not true. The sulfur binds only to tantalum, and the selenium binds only to the tantalum, and so we have a very beautiful graded structure, and you can see that the slicing that I mentioned with FIB, you see how the tantalum binds to selenium mostly, and first of all, the tantalum and the lanthanum form a beautiful misfit nanotube structure, and then the selenium and the sulfur are absolutely different or segregated, although we work at 1,000 degrees C, and there is no, the entropy effect is much smaller than the enthalpy effect. So I think that with that I can conclude my talk. I would just mention the work of the late Lila Panchakarla, a former postdoc of mine who passed away 2 years ago, and he produced beautiful tungsten, lanthanum oxide, calcium oxide, cobalt oxide, misfit nanotubes, using similar concept, hydrothermal reaction, and these nanotubes have very interesting physical effect. I won't have time to describe them, but I want to mention them in relationship to Lila Panchakarla's performance and unfortunate untimely death. So with that, let me conclude my talk, and I thank you for your attention, and if you have questions, I'll be happy to answer them. Okay. So basically, the measurement that I showed was a magnetic measurement, so it's basically a Meissner effect. And because we could not establish a contact on a single nanotube, and we could not make electrical measurements on a single nanotube. But in a previous paper that we published with Ivasa, we contacted single tungsten disulfide nanotubes. His group made electrical gating using liquid ionic gate, and they measured beautifully the superconducting of tungsten disulfide nanotube, single nanotube, and furthermore they showed the diameter dependence of the superconducting transition. Of course, this was electrical measurement, but not magnetic measurement. So we were never able to publish a work where we both saw the magnetic and the electrical effect, and superconducting effect. But in the case of the electrical measurements with Ivasa, we beautifully showed the little Parks oscillation of the Cooper pairs that are going in phase, basically, preserve their phase and interfere with themselves and form, as a function of magnetic field, minima and maxima. So this is a beautiful demonstration of 1D superconducting transition.